So if you look in Blackhout et al. From 1979, there's a suggestion on how you can deal with the pointing error of a telescope. That's the 60 seconds over the magnification, and that gives you a variation in the line of sight according to the ability to point. So you propagate that over the length of sight, and that gives you a variation in the rod reading. And then you have a similar variation directly with the 0.2 arc seconds over the length of sight, would give you a variation in the rod reading. And you take those two as variances, combine them, take the square root, and that gives you a variation in a single rod reading as a consequence of pointing and leveling error. And in this particular case, it's double scale invar staves, so that means there's twice as many readings taken because you use the left and the right scale. So there's an improvement by a factor of 2 because you take the average, but then you have an increase by a factor of root 2 because it's a height difference where you take the backside rod readings minus the foresight rod readings. And that's how the delta H plus or minus 0.035 came about. And then if you take it over 2 measurements, that's the 0.049, and then if you take the 0.049 over the 20 meters, that's an angular equivalent of plus or minus 0.5 seconds. And that's following an example, but it's really, that part of it is really more related to the engineering surveying, which is the third topic. So that's study question 12. And there was also a forum discussion on study question 15. And that's our friend, the refractive index, where that's a very familiar looking formula, and probably this was a better one to look at relating to the earlier study question. And you'll notice again, this is the one that was reflected in very often in the exam formulas, where the N sub D is the design refractivity, N sub I is the actual refractivity. And you'll notice that when you evaluate that at 12 and standard pressure, it becomes 0. So then it's a case of evaluating that for the temperature of 30 Celsius and 1,000 millibars. And then how would that vary with the 2 parts per million? And this is where this business of taking the average from the 2 ends would come into it. Well, let's go to the second part, and if you had to measure the temperature to within 2 Celsius degrees and the pressure within, say, 7.5 millibars, how would you do it? And there is a discussion in Ruger's EDM book about that, and that's really starting to get into the instrumentation testing and utilization topic area, which will be the next session's concern. But it is to some extent a design problem because you have to determine the temperature and pressure, and how do you do that? And it's usually then a problem of wanting to be sure that the sampling is along the path. So obviously the thermometer shouldn't be in your pocket, it should be out where the radiation is traveling, but it should be shielded from the effects of solar radiation. If we talk about accuracy rather than precision, then we have to be sure that the temperature is really the temperature and the pressure is really the pressure. So that means calibrating the thermometer and calibrating the barometer that's being used, and also recognizing the fact that when we do measurements, even if it's only at the two ends of the line and take the average, we have no guarantee that what we have sampled there is what the radiation has experienced. And the most obvious example is if you're measuring across a river valley and you take the temperature and pressure at each end, which is on land, and yet the radiation is going over water and all sorts of different terrain and everything else, so that the actual conditions that the radiation experiences will be quite different from what you're actually sampling. So that was study guide question 15. And the next one is at the very tail end, number 30. If we talk about accuracy rather than precision, then we have to be sure that the temperature is really the temperature and the pressure is really the pressure. So that means calibrating the thermometer and calibrating the barometer that's being used, and also recognizing the fact that when we do measurements, even if it's only at the two ends of the line and take the average, we have no guarantee that what we have sampled there is what the radiation has experienced. And the most obvious example is if you're measuring across a river valley and you take the temperature and pressure at each end, which is on land, and yet the radiation is going over water and all sorts of different terrain and everything else, so that the actual conditions that the radiation experiences will be quite different from what you're actually sampling. So that was study guide question 15. And the next one is at the very tail end, number 30. Now there was also, I think, in the forum related to this topic area was with respect to a couple of exams. And unfortunately I don't have them immediately handy. October of 2004 and October of 2008. I could maybe offer some verbal comments about them. Okay, 2004 October, and it was question 2, which was taking a three-dimensional traverse where you're measuring vertical circle readings and heights of instrument and heights of reflector, and having to reduce them mark to mark. If you do a foresight from, say, A to B, and then you occupy B and do a backsight onto A, the distances, the zenith angles, and won't be compatible because you will have different heights of instruments. So you have to take those values and reduce them to mark to mark. So this is the one that I was just mumbling about, and there had been questions about it on the forum. So basically what's explained in the paragraph before question portion A is this business of setting up on A, sighting B, and vice versa. And you have different heights of instrument and different heights of reflector at the two occupations. So if you take the slope distance from A to B compared to the slope distance from B to B, or the zenith angle at A to B, or from B to A, or the right triangle that's created opposite the slope, they won't be the same. And this is primarily because you have different heights of instrument. So you can't take the right triangles directly. And what would you do about it? Well, typically you would reduce each occupation to a mark-to-mark slope distance, mark-to-mark zenith angle, and mark-to-mark difference in height from the ground mark to the second ground mark.